Hey, what's up, guys? I have something that will absolutely blow your mind. This is the computer playing Super Mario Bros. And guess what? The computer has no knowledge about the internal state or the mechanics of the video game. Rather, it's simply looking at the frames and then deciding what buttons to press. Exactly how humans do it. Impressive, right? Well, if you want to learn how to implement this, stay tuned because that's exactly what I'll be sharing with you guys today, and I cannot wait. This was done using a subclass of machine learning algorithms called reinforcement learning. Reinforcement learning is the coolest thing ever. In fact, it's been used to train drones and robots, find more efficient ways for matrix multiplication, and even make the training process for other machine learning algorithms faster. Oh, and not to mention, it was also used to train everyone's favorite chatbot, ChatGPT. Reinforcement learning is pretty different from its cousins supervised and unsupervised learning. In supervised learning, the model is given a dataset where each point has a correct answer associated with it, whether it's categorical or numerical. The model's job is then to predict these values accurately. In unsupervised learning, the data points don't have a correct answer, but rather the model's tasked with extracting general trends or insights. Reinforcement learning is its own beast. The objective of reinforcement learning is for the agent to maximize its rewards inside of the environment. We give the agent a positive reward whenever it exhibits behaviors we want to persist, and negative ones for behaviors that we don't want. It's kind of like teaching a dog new tricks. Another thing to note is that in supervised and in unsupervised learning, you must have the data pre-collected before you feed it to the model. Whereas in reinforcement learning, we'll see today our agent go out into the world, collect its own experiences, and then learn from it. It's a completely different paradigm when it comes to training. I wanted to share an implementation of the DDQN algorithm, or the double deep Q network. I'm not going to dive into the nitty-gritty of reinforcement learning theory. I'd rather just share a more intuitive understanding for those that have a base level understanding of machine learning but haven't really been exposed to reinforcement learning before. However, for those that are interested, I'm going to leave some of my favorite reinforcement learning resources down in the description below, along with the paper that originally pioneered the double deep Q network algorithm. I first implemented this algorithm when I was a sophomore in college, and I still remember the excitement that I felt when I first watched the model start to train, learn, and eventually beat the level. I was absolutely awestruck. I mean, I understood all of the math and each line of code that I wrote to implement the algorithm. However, there's just something that's still magical about reinforcement learning that gets me excited every single time. And my goal today is to be able to package that excitement and share it with you guys through this video. Let's start off with the basics. In order to understand the fundamentals of reinforcement learning, we need to define these following terms. Let's understand each of them in the context of Super Mario Bros. First is the agent. The agent today will be our neural network that's controlling Mario. It's the one responsible for making decisions and taking the optimal action. The environment is what our agent will be interacting with. It's going to be level 1-1 of Super Mario Bros. On the NES. A state is a snapshot of the environment at any given time. It's essentially what our agent sees. Today we'll be using 4 consecutive frames from the game. The reason we're using consecutive frames is so our agent can see motion. For example, is the Goomba coming towards us or away from us? Well, for us to know, we need to know the previous frames. Oh, well, hopefully our agent knows to jump. Actions are the inputs that the agent has available to it to give to the environment. Today, the agent will have access to these 5 button combinations to press. First one is with no buttons pressed, and then the agent's able to move right. A is used to jump, and the longer it's held, the higher Mario will jump, and then B is used to move faster. Once the environment gives the agent a state, and the agent responds with an action, the environment also gives the agent a reward. A reward essentially helps the agent determine whether or not the action it took inside of that state was good or bad. Today, we'll be giving the agent a +1 reward for each unit to the right that it makes in the video game. It'll receive a -1 reward for each second that passes by in the game's clock. This is to disincentivize the agent from standing still. And then the agent will get a massive -15 points if it dies. Now, the concept of a negative reward may seem foreign to some. However, remember, the goal of the rewards is to guide the agent to optimal actions, and negative rewards still help the agent do just that. Everything that we've talked about so far is summarized in this diagram. It essentially outlines how the agent and the environment interact with one another. The agent gives the environment actions, and the environment returns states and rewards. An episode for us today will just be one attempt at the level. An episode will end whether Mario dies, reaches the flag, or runs out of time. A policy is a function that takes in a state and returns an action. It's what our agent will use to make its decisions. Some reinforcement learning algorithms will have the policy be a probability distribution. However, today in our DDQN algorithm implementation, we'll be using the Epsilon-Greedy approach. More on that later. A value function takes in a state and returns how valuable that state is. In reinforcement learning, it's natural to view some states as more valuable than others. For example, the state where you're right next to the flag is probably a little bit more valuable than the one where you're falling down a hole. We're not going to be working directly with the value function today. However, I thought I'd mention it because a lot of other reinforcement learning literature brings it up. An action value function takes in a state and an action and then returns how valuable this pair is. As you can see on the screen, this state action pair is probably more valuable than this state action pair. I'm sure you can see why. Approximating this function accurately today is our goal because it's going to let our agent take the action inside of a state that has the highest value. Alright, quick review. We're using reinforcement learning to train the computer to play Super Mario Bros. Our agent, or the neural network that's controlling Mario, will receive a state from the environment. Remember, a state is 4 consecutive frames from the video game. The agent will then take an action. If the action was good, we'll give it a positive reward. If the action was bad, we'll give it a negative reward. And then the agent will use these rewards to train itself over time to take better and better actions. Eventually, we're hoping that the agent will learn how to beat the level and reach the flag that's waiting for it at the end. That was a lot to take in. Thank you guys for bearing with me. We have 3 more concepts to cover. First is the Epsilon-Greedy approach. Second is the replay buffer. And third are some more details about the action value function. After that, we'll assemble the algorithm and then implement it in code. The Epsilon-Greedy approach is the strategy our agent will be using today to choose its actions. However, to understand Epsilon-Greedy, we first must take a step back and understand the explore-exploit dilemma, a problem that's at the heart of reinforcement learning. Let's say our agent has learned that jumping over Koopas is the most effective way to not die. Good, I guess it gets the job done, right? However, as I'm sure my fellow gamers know, that jumping on a Koopa actually turns its shell into a weapon that can be used to eliminate other enemies. If our agent constantly exploits, or takes the action that it deems to be the best in the current moment, then it'll never get a chance to explore other potentially superior strategies. So how do we navigate this explore-exploit dilemma? Enter the world of the Epsilon-Greedy approach, a clever solution to the explore-exploit dilemma. With probability epsilon, our agent ventures into the unknown, taking random actions. And with the remaining probability, 1 minus epsilon, it'll take the action that it's confident is the best one. It's essential to note that this best action of the agent is dependent only on what it knows in the current moment. It's not necessarily the best action overall. Initially, when our agent knows nothing about the environment, we'll set epsilon to 1, ensuring maximum exploration. And then over time, as our agent continues to learn about the environment and its dynamics, we'll start to taper off epsilon from 1 to a very small non-zero number. We'll always keep epsilon greater than 0, just so our agent is always on the lookout for new strategies. This means that if our agent did learn to jump over Koopas, we're hoping that with the Epsilon-Greedy approach, it'll eventually randomly jump on one, and then realize the benefits of doing so. Now let's cover the replay buffer. It's essentially a storage for our past experiences and rewards. It'll be used to train the neural network. There are a couple of reasons why we use a replay buffer rather than training on the experiences as we collect them. The first is because sequential experiences have a lot of correlation, which can lead to a lot of instability when training the model. To eliminate this instability, we randomly sample from our replay buffer. And the second reason is that we're now able to reuse data, which actually improves data efficiency. In the replay buffer, we'll be storing tuples of the state, action taken, reward received, next state, and a Boolean flag indicating if the episode is done for any reason. We'll see how each of these come into play when we sample the replay buffer to train our network. Now, let's pull up the action value function that we mentioned earlier. This is often referred to as the Bellman equation. Remember, our primary objective today is to approximate this function, enabling our agent to make optimal decisions in any given state. The goal isn't just about seeking immediate gratification. Instead, the agent aims to maximize its rewards over the long run. Humans intuitively do this as well. For example, we may take a slightly longer route with less coins if it leads us to an item box at the end that contains the invincibility star. Math notation is scary, so let me translate this equation to English. The value of taking action A in state S is equal to the reward you get in the next time step plus the value of taking the best action in the next state S prime, multiplied by a discount factor. The discount factor makes rewards from future states less valuable. In reinforcement learning, this is important because future rewards are less predictable than the current one due to the environment's stochastic nature. In the Stanford marshmallow experiment, children were given a marshmallow and were told that they could either eat it right now or wait 15 minutes for a second marshmallow. It was to measure their self-control when it came to delayed gratification. Essentially, the researchers were measuring the children's gamma, or their discount factor, 1 marshmallow now, or 2 in the future. Our agent is kind of in a similar situation, except for the children, their second marshmallow was guaranteed. Unfortunately, our agent does not have that luxury. As such, it's ideal for it to value a guaranteed marshmallow in the present more than a potential marshmallow in the future. A gamma of 1 means that there is no discounting, while a gamma of 0 means the agent is completely myopic. We want neither, but rather to strike a balance between the two. This action value function is recursive in nature. This means that the value of a specific state action pair is not just based on the immediate reward. Rather, it also depends on the value of the subsequent state action pair. Dive deeper, and you'll see that this subsequent value, in turn, depends on its immediate reward and the value of the next state action pair, and the chain continues. We assume that we take the optimal action, the action with the highest Q value, at each recursive level, thus the max function. When you unravel this recursive structure, you'll find that the value of any state action pair is essentially the sum of its immediate reward and the accumulated discounted future rewards until the end of the episode. This first equation, once you assume you're taking the best action at each time step, condenses down to this after you distribute the gammas appropriately. The further out a reward is, the more times it's multiplied by gamma. Still a little bit confused? Don't worry, I was too when I first learned this. Let's try to tackle this from a more visual approach. Take each ribbon on the screen to be a reward the agent will get until it reaches the flag. Remember that these rewards are granted after each step the agent takes in the environment, and the number on the screen is arbitrary. The ribbons are getting progressively smaller to signify the discounting. Assuming the agent is currently in state S and takes action A, the value of this state action pair is the sum of this entire sequence of rewards, discounted appropriately. If S prime is the next state after taking action A in state S, and A prime is the best possible action in S prime, then the value of S prime A prime will be this sum, again discounted appropriately. We know the reward R we got from going from S to S prime, so we can use that to help tune the estimate of the current state action pair's value. To train our agent, we compare its predicted value of a state action pair to the target value. Remember, the target value is the immediate reward from a move plus the discounted value of the best possible next move. Essentially, we compare its predicted value of the sum of these ribbons to the predicted value of the sum of these ribbons, plus the ribbon whose value we know with certainty because the agent just received that reward. While both the prediction and the target are estimates, the target is considered to be more reliable. Why is that the case? Well, because the target is based on fewer future assumptions. As a component of the target is the reward directly observed from the agent's recent action, making it grounded in immediate experience rather than speculative projection. Once we have our predicted value and our target value, we can use the following equation to update our estimate. For those of you familiar with gradient descent, you might recognize this to be exactly that. Alpha is our learning rate, or the size of the steps our network's parameters take as they converge towards their optimal values. The part inside of the square brackets is the error, or the difference between our predicted and target values. This is exactly the derivative of the mean squared error loss function. I'm sorry if all of that was overwhelming. I know it was for me the very first time I learned it. However, the intuition of the action value function is the hardest part. I swear, it gets easier from here. So how do we even begin to approximate this function that has such a vast space of potential state action pairs? Well, we turn to our friend the neural network. Remember, neural networks are great at approximating functions in extremely high dimensions. The specific architecture we'll be using today is the convolutional neural network, or a CNN. CNNs excel at extracting meaningful visual features from its inputs, whether it's enemies, holds, or the flag. If you're not too familiar with CNNs, I highly recommend NVIDIA's Learning Deep Learning book. It'll cover literally everything you need to know about CNNs. The input size will be the dimensions of our state, which we'll see in just a sec. The number of neurons in the output layer will be the number of actions available to us, which in this case will be 5. The value in each neuron represents the predicted Q value for that associated action paired with the input state. When running this algorithm, we're actually going to have 2 identical copies of our neural network. The first one will be the online network. This is the one that we'll actually be training. The second one will be the target network, the one we'll be using for the ground truth for our predictions to give to our loss function. The target network won't be trained. However, we'll be intermittently copying the weights from the online network over to the target network. This is to increase stability during the training process. To train the online network, we sample the replay buffer to get a random tuple containing a state, action, reward, next state, and done flag. We then pass in the state to the online network to get the predicted Q values for the 5 actions. The different sized controllers represent how the network values each action differently. However, we only care about the action that was taken and is present in the sampled tuple. This is our predicted value for this state action pair. To see how accurate it is, we calculate our target value. To do so, we pass in the next state into our target network to get the predicted Q values for the 5 actions again. This time, we take the highest predicted Q value represented by the largest controller. To compute our target value, we take the reward from our sample and add it to the predicted Q value of the next state multiplied by gamma, our discount factor. We would then pass these 2 values into our loss function and perform one learning step for our online network. This technique is known as bootstrapping because our poor little network is essentially pulling itself up by its bootstraps. It's using a crappy target network to train our crappy online network. And then as the online network improves just a little bit, we'll copy over the weights from the online network to the target network. And now we're using a slightly less crappy target network to continue training our online network. We'll repeat this process tens of thousands of times, and eventually we'll start to see our agent actually start to learn. I know this seems very jank, like we're using a moving estimate to train another estimate. However, in reality, we'll see how stable it actually is. So let's put together all of these moving parts and finally assemble our DDQN algorithm. We start off with initializing our starting variables and resetting our environment, which gives us the starting state. Second, given the state, we'll choose an action with our Epsilon-Greedy approach. Third, we'll use this action to take one step inside of the environment. As mentioned previously, the environment will return a new state and a reward. We'll then take the current state, action, reward, the new state, and the done flag and store them all in our replay buffer. Then we'll do one learning step, which involves sampling the replay buffer and training the online network. Then we'll take our next state and assign it to our current state. We'll repeat all of this until the episode is done. And finally, we'll repeat this inside loop for however many episodes we want to train for. So let's finally get to coding this up. For the NES emulator, we'll be using a library called Gym Super Mario Bros. It handles all of the complexities of the emulator side of things for us. It gives us neatly packaged Python objects for the states, along with a simple way to input actions. It does this via a simple API that's based on OpenAI's Gym API. OpenAI's Gym library is a wildly popular collection of different reinforcement learning environments that researchers or enthusiasts like us can use to try out different algorithms. They're incredibly easy to set up and use. These days, the most common approach is to use Gymnasium, which is a maintained fork of OpenAI's Gym library by an outside team. I wonder what OpenAI is working on these days. Also, all of the code will be linked on GitHub right down in the description, and if you ever need to reference it throughout this video or even afterwards, please feel free to do so. So let's start off with a simple example. Let's first import the libraries. We'll be limiting our agent to only press these following button combinations, which is why we're importing write only. Then we create our environment object and wrap it with the joypad space wrapper, ensuring that the actions in write only are the only ones the environment can accept. Then we set our done flag to false and reset our environment. This while loop will run for as long as the agent is still alive. First, let's have our agent only press write on the D-pad. We'll then take one step in the environment with that action and get our done flag, ignoring the other return values from the step function for now. And finally, because on line 6 we have our render mode set to human, calling env.render will display our environment to our screen so we can see what our agent is doing. As expected, our agent is not doing so well. To add some dynamism, let's have it randomly choose an action from our action space. Unfortunately, our agent still sucks. Good thing we have an entire reinforcement learning algorithm up our sleeve. Let's implement the wrappers first. Wrappers are essentially a way that we can modify our environment's outputs. If you want some more information about writing your own wrappers, I highly recommend checking out the Gymnasium Documentation, which is linked below. We're going to be using 4 different wrappers today. The wrapper we're implementing will skip frames, meaning it'll just take the action inputted for the first frame and reapply it for however many frames we want to skip. We'll aggregate the rewards over those 4 frames. This is useful for us because consecutive frames have a lot of overlap, so it's redundant to reprocess everything. The next 3 wrappers are already implemented by Gymnasium. Resize observation will change the dimensions of a frame from 240 by 256 pixels to 84 by 84. This is just to reduce the computational load. Similarly, grayscale observation will turn the frame from having a red, green, and blue channel to just 1, reducing the amount of data our network will have to crunch. Finally, so our network can see motion, we're going to take 4 consecutive frames and stack them on top of each other to finally create our state object that will pass into our network. Each final state object, comprised of a stack of 4 processed frames, encapsulates data from 16 original game frames due to the combined effects of frame skipping, resizing, and stacking in our pre-processing steps. The code for the wrappers is pretty straightforward as we're only implementing one of them. We first override the constructor to take the number of frames to skip. Then we override the step function. Whenever step is called, we use the for loop to take skip number of steps, aggregating the rewards. The apply wrappers function applies our wrappers one by one, encapsulating our base environment like the layers of an onion. At the end, it returns our fully wrapped environment object. We'll use this function in our main.py. Let's next create our neural network with PyTorch. As mentioned previously, we'll be using a convolutional neural network. We're going to have 3 convolution layers followed by 2 linear layers. The input shape will be 4 by 84 by 84, which is the dimensions of our state. The number of actions will be 5. The underscore get conv out function performs a dummy forward pass through the convolutional layers to get the number of neurons we need in our first linear layer. It's 3136 with this specific architecture, but the function allows us to dynamically calculate it were we to change anything in the future. The freeze flag allows us to prevent PyTorch from calculating the gradients, which we'll need for the target network. Remember, we only use the target network to calculate the correct values we want our online network to predict. Then finally, we add our forward pass and then move the network to whichever device we're training on, whether it's the CPU or GPU. Let's next create the agent class. These will be our imports. Along with PyTorch and NumPy, we'll also import our neural network that we just created. For the replay buffer, we'll be using PyTorch's built-in TensorDict replay buffer, which will hold Python dictionaries with tensors as the values. The storage mechanism it'll be using is PyTorch's lazy memmap storage, which will use memory-mapped files for easy access to our experiences, along with alleviating RAM usage. We could have just used a Python list for our experiences from which we sample, but that means sampling would be really slow and we'd be using a lot of RAM. For the constructor, we'll take in the dimensions of our state and the number of actions our agent has access to. We'll also use a learn step counter, which keeps track of how many times we've trained our network. We then set up our hyperparameters. First is the learning rate, or alpha. This is the size of the steps the network will take when it's updating its weights. Second is gamma, which is our discount factor. Remember, we want the agent to discount future rewards. Third is the starting value of epsilon, which will be set to 1 initially to encourage exploration. Fourth is the epsilon decay factor, which will multiply epsilon with after every time step. Fifth is our minimum epsilon, so we always maintain some likelihood to explore. Sixth is the batch size for our training, and finally is how often we'll sync the target network weights with the online network. After the hyperparameters comes the networks. Again, making sure the target network's parameters are frozen. After adding our optimizer and loss, we create our replay buffer with the capacity to hold 100,000 experiences. Then, let's write our choose action function that uses the Epsilon-Greedy Approach. As we can see, when the random number is less than our epsilon value, it'll choose a random action. Since epsilon starts off at 1, the action chosen will always be random. As the value of epsilon decays, the probability of using our online network to choose the action with the highest Q value increases. Also, because we want the index itself, not the estimated value of that action, we're taking the argmax. Our decay epsilon function multiplies the current value of epsilon with our decay factor and ensures it doesn't go below the minimum epsilon threshold. The store in memory function takes in the tensors that we want to put into our replay buffer, organizes them in a dictionary, and adds them to the buffer. The sync networks function checks if enough learning steps have passed, and if so, it'll copy over the weights of the online network to the target network. Now, for the most important function, the learn function in the agent class. We first validate that there are enough experiences in our replay buffer to sample a batch from. Then we call the sync networks function. We then clear our gradients, followed by sampling the replay buffer. We store the results in the states, actions, rewards, next states, and dones variables. We pass the states tensor through the online network to get our predicted values. We index by the actions that we actually took because we only perform backpropagation on those values. Then we calculate our target values. We pass in the next states through our target network and get the value that the best action yields. We then multiply it by gamma and add it to the rewards we got in the current state. The 1 minus dones part sets all future rewards to 0 if we're in a terminal state. We then calculate the loss using our predicted and target Q values, performing backpropagation to calculate the gradients, and then perform a step of gradient descent with those gradients. We also then increment our learn step counter and decay epsilon. Finally, let's create our main.py. In this file, we'll set up our environment as we saw previously, and then create the full training loop. Again, starting off with our imports, this time adding our apply wrappers function and our agent class. We then create our environment, applying the joypad space wrapper plus the other 4 that we talked about earlier. We also create our agent object and pass in the dimensions of our state and the number of actions from our environment. Finally, the training loop looks very similar to our pseudocode. For each episode, we collect experiences and learn from them until the episode is done. First, we choose an action given the starting state. Again, this will be completely random at first. Then we take a step in the environment and store the state, action, reward, new state, and done flag in our replay buffer. We then perform one learning update. Then we set our current state to our new state and repeat. Fair warning, training for 50,000 iterations can take a while. I have an RTX 3080 and it took me about 2 days of training nonstop. However, I'm excited to see what optimizations you guys can uncover by tuning the hyperparameters. But now, the moment you've all been waiting for. After we finish training, this is the final result. Well, we did it, guys. We finally trained the computer to play Super Mario Bros. I hope you guys feel the magic of reinforcement learning that I've always felt. In fact, even bigger than that, I hope you realize that machine learning is so much bigger than just predicting labels from a dataset or trying to cluster some points. Anyways, if you have any questions about anything that we talked about today, please leave a comment down below. And until then, see you guys next time.